Welcome to Math TV with Professor V. In this video, we're gonna look at how to find volumes of solids of revolution by slicing them. Another name for this topic is using the disk and washer method to find volumes of solids of revolution. So the reason why we have two different cases, disks and washers, depends on what sort of solid emerges after spinning a given region about an axis. So what the heck am I even saying? I know. So in all of these problems, you're going to be given some region in 2D and then told to spin it around either a horizontal or a vertical line. And as you can see here in this first case, we have a solid with no holes in the middle. So when we slice this solid, okay, each of the slices looks like a disc. And so in order to compute the volume of this solid, we want to add up the area of each of these little discs. And the area of a disc is pi r squared. It's basically a circle. And so if we add them all up by integrating from a to b, pi r squared dx, then we get the volume of this solid. Now, in some cases, the region that you spin will have some gaps in it. So this part is open space, all in the middle. It's hollow. So we were given some region here, spun it around the x-axis in this case, and then now when we're slicing, each of the slices is not a solid disc, but it's a washer. You see, if you've put together any pieces of furniture from IKEA, you're probably familiar with them. So there's this little hole in the middle. So again, same idea. We want to add up the area of all of these washers, but we have to subtract the area of this little baby hole in the middle. So pi capital R squared, that's going to give us the area of the larger circle here. Pi baby r squared subtracts out the middle hole. Hence, this is our washer. Okay? When you're using this method of slicing for discs and washers, keep in mind we always slice perpendicular to the axis of rotation. So if you're spinning around the x-axis, then your slices are perpendicular to the x-axis. And notice the slices are moving in the x direction, which is why we integrate with respect to x. If we spun around a vertical line, then things would be different. And we'll look at a bunch of examples on this topic. Now, I just gave a very general, brief recap of the idea. If you want a little bit more thorough of an explanation, I have the original intro video lecture linked up here. Click in the top right. It's in the description too. But if you're like, I'm good, I just want to see a bunch of examples, then I got you. That's what we're going to do the rest of the video, okay? Hop to it. First one, find the volume of the solid generated by revolving the shaded region about the given axis. And they told us here we're going to spin it around the x-axis. All right, so I always add a little symbol like so to indicate what we're revolving around, and you got to draw a graph. So here's the original region. Fabulous. I'm going to do a sketch of the 3D solid that results. So basically just reflect the region over the x-axis, 1, 2, 3, 4, and kind of mirror it like so. All right. You can add a little more dimension if you want. Sometimes it gets messy if you add too much. And let's figure out which variable we'll be integrating with respect to. So if we're spinning around the x-axis, I'm going to slice perpendicular to the x-axis, and notice the slices are moving horizontally. They're moving in the x direction. So let me draw a slice of this solid. It would look something like this. Let's shade it in. Okay, and I can see there's no hole. So I have a disc right here. Do you agree? This is a disc. So to compute the volume, I'm going to have pi. I like to put it outside. I know originally the formula up above it was inside the integral. No need. Pi AB, we just have r squared dx. So we need to identify r, a, and b. So the radius is going to go from the center of the disk to the outer edge. Okay, this is the radius r. Now, you might be able to identify it pretty easily right now, but I'm going to teach you a way to do it that will apply for even the most complicated of examples, okay? Notice the radius is bounded on top by this curve here. Who is that curve? 4 secant x. And on the bottom by, what is this? Well, it's just the x-axis, y equals 0. So I want you to just always get in the habit when you're finding the radius, if you're integrating with respect to x, do top minus bottom, just like when you did areas between curves. So who's bounding r on the top? This is top, 4 secant x, minus on the bottom is 0. It's always y equals. Notice, y equals 4 secant x, y equals 0, and that's because we're integrating with respect to x. So these have to be functions of x. So this is 4 secant x. That might have been obvious. It might be a little overkill, but I told you things are going to get spicier in a hot second, so just stick with it. Also, we have to figure out a and b, limits of integration. They have to be limits for the variable that we're integrating with respect to, in this case, x. So look at the original region. What are the bounds for this region in the x direction? It goes from 0 to pi over 4. So that's a and b. So this is equal to pi integral 0 to pi over 4 secant of x squared dx. How are we doing? Very good. Okay, let's clean up and then integrate this bad boy. So we've got pi integral 0 to pi over 4. Squaring everything, we have 16 secant squared x dx. Antiderivative of secant squared x is tan x. The 16 doesn't do anything. In fact, let's take it outside with the pi. And then I'm going to have tan x evaluated from 0 to pi over 4. Remember, the derivative of tangent is secant squared x, so that's why when we go backwards, that's the antiderivative. Leave 16 pi outside. Let it mind its own business while we're evaluating these limits of integration. We're going to have tangent of pi over 4 minus tangent of 0. Do you know tangent of pi over 4? Oh, I hope so. It's 1. And tangent of 0, 0. So I just have 16 pi times 1 minus 0, so this is 16 pi. Remember, this represents a volume, so technically it's units cubed. I don't require my students to do that, but it's so important to keep in mind, like, what did I just find? What does this represent? It's a three-dimensional quantity. How was that one? Okay, that's a nice little, that's a warm-up. I have 5 in total. I hope you loved them all. I certainly did. These are all from the practice test if you're in my class. Okay. Here's another region, and we're spinning it about the x-axis again. Notice this is going to look a little different. Okay, so start off, revolve the region about the x-axis by initially just reflecting what you see here over the x-axis. So just kind of copy. It's going to go up here, swoop in a similar way. And then if you want to fill in some shading or whatnot, okay. You can add more dimension. Don't get too carried away though. Then it's going to look like a hot mess, you know? So it's kind of like, it's looking like a sideways bowl, right? If you turn your head. Now let's figure out, we're going to integrate with respect to which variable. If we're spinning around the x-axis, we slice perpendicular, and look, the slices are moving in the x direction. Like I typically only draw, you know, one slice, but there's many. That's why we're integrating, because we're adding up infinitely many slices. Here's a slice right here. You could have another one a wee bit further down. It's going to look disgusting because it's going to get messy, so I'll erase it, but just you get the idea, yes? Okay, very good. Now notice here the slices are not solid all the way through. So I have a washer. Let me shade in the washer like so. Please make sure your graph makes sense, okay? So the washer needs to be bounded on the outside by the outer function and on the inside by the inner function. Don't have it floating in open space. What is that? That's nothing, okay? Don't draw such nonsense. And we already decided we're gonna integrate with respect to x. Okay, beautiful. Now in this case, we have to figure out what's big R, the outer radius, and little r, the inner radius. Because volume's gonna be, let's take the pi out, please. A to b, big R squared minus little r squared dx. All right, let me zoom in. I'm gonna draw big R for you, okay? So outer radius is gonna go from where we revolved all the way to this outer edge. That's big R, this whole thing. Okay, I don't love that arrow. Let's redraw. That's big R. Okay, plus this is bothering me. So let's see, can you determine big R, capital R? What's bounding it on the top? What's bounding it on the bottom? On the top is y equals 16. On the bottom is y equals 0. So big R is just 16 minus 0, or 16. Can you see it? And remember, I drew another washer over here. The outer radius would still be the same, 16. If you look at the solid from the outside, it's just going to look like a regular cylinder, right? With radius 16. It's only once you look inside you see, oh, stuff has been scooped out. Okay, now what about little r? Little r I'll do in this pink color. Here's little r, okay. That's little r. Again, top minus bottom. What's bounding little r on the top? This curve here, who is that? That's y equals 16 minus x squared. Who's bounding little r on the bottom? Y equals 0, the axis of revolution. So we have 16 minus x squared minus 0, which is just 16 minus x squared. Okay, very good. So now we're ready to put everything together. Do you know what our limits of integration are from A to B? Always look at the original region before you spun. And since we're integrating with respect to x, what's bounding the region in the x direction? It's from 0 to 4, right? So here we go. So v equals pi times the integral from 0 to 4. Outer radius squared, that's going to be 16 squared minus inner radius squared. 16 minus x squared squared dx. Beautiful. This is just going to be a relaxing little polynomial once we multiply it all out. So 16 squared, that's 256, minus expanding 16 minus x squared squared, that's going to be 256 minus 32x squared plus x to the 4th dx. And then now I'll distribute the negative. We have pi times the integral 0 to 4. These 256's will cancel out, won't they? Yes, Professor V. Okay, good. So then we have 32x squared minus x to the 4th dx. And then now, time to anti-differentiate. Leave the pi outside. It's minding its own business. 32 over 3 x cubed minus 1/5 x to the 5th. All evaluated from 0 to 4. Excuse me. And then let's plug in our limit. So pi times, this is going to be 32 over 3 times 4 cubed, that's 64, minus 1/5 times 4 to the 5th, and then minus lower limits 0. And then you can clean this all up. You should get 7,168 pi over 15. Okay, very good. If you're in my class, don't worry. I'll make the numbers smaller because you won't have a calculator, so no stress. That's too big, too big. I wouldn't want to get you all worked up in the middle of an exam. Okay, how are we doing? We're gonna take the spice level up momentarily. Here we go. Find the volume of the solid generated by revolving the region bounded by the given lines and curves about the x-axis. You must include a clearly labeled sketch of the region, most certainly. So this time they're not giving us the graph. That's fine. You should be able to graph, what is this, just a few lines in Calc 2, I would certainly hope. We're still spinning around the x-axis. We'll switch that up in a minute, but one thing at a time. So I can see this is the equation of a line, this is the equation of a line, this is the y-axis. Let's figure out where these two lines intersect so we can draw an appropriate graph. Always do that first. Intersection. So when does negative 7x plus 14 equal 7x? Let me add this negative 7x to both sides. So 14 equals 14x. So that happens at x equals 1. If x equals 1, then y will be 7. So these two lines intersect at 1, 7. And then I'm looking here, this first line has a y-intercept of 14. Okay, scale in a way that makes sense. You don't need to scale the x and y axes in the same way. And so I don't really want to pull this x-axis out so far. All of the action is happening at 1, here's 1. And then I'll just say this is 7 and this is 14. And there's nothing wrong with that because my graph's going to look fabulous. So let's graph negative 7x plus 14. It's going to have y-intercept right there, and then it's going to intersect the other line over here. And it keeps going, right? Okay, if you want to keep drawing it, there's negative 7x plus 14. And then positive 7x, that's going to intersect right there. It goes through the origin. That's just 7x. And then we also have x equals 0. Well, that's right here, the y-axis. Okay, can you see what region is bounded by all three of these curves? Well, they're lines. That's why it said lines and curves. Can you identify it? It's this triangular region, right? So you have to use all of the given lines and bound a region. So sometimes students get confused. They think this is the region we're spinning. But no, nobody told you to use y equals 0, did they? They said use x equals 0. Well, that's right here. Okay, you don't have to leave this part here, the excess, but whatever. It's there. I'm not mad about it. But you only need to really draw what's relevant. And we're spinning this around the x-axis. Okay, great. So let me just kind of gently reflect what's going on. We have something looking like this. And then I'm going to slice perpendicular to the axis of revolution. So if I slice perpendicular, the slices are going this way. Notice my slices are moving in the x direction, so I'm going to integrate with respect to x. Let's draw a washer. Did you notice we have a washer? Because there's definitely going to be a hole in the middle. Okay. Here, I'll color it in green. And then let's see if we can identify outer radius and inner radius. Okay. So outer radius, inner radius. Let me draw the outer radius for you. It's going to go from the very outer edge all the way to the center. That's big R. Okay, again, think top minus bottom. Who's bounding it on the top? This is negative 7x plus 14, right there. Who's bounding it on the bottom? Y equals 0. So negative 7x plus 14 minus 0, so just negative 7x plus 14. What about little r? Little r. Always look at the original region, otherwise you're going to get screwed up. I should have said this sooner. Don't look over here to find big R and little r. It will get you messed up. Look at the original region only. Okay, little r. From here to here, yes? There's little r. Who's bounding little r on the top? 7x. Who's bounding little r on the bottom? 0. y equals 7x, y equals 0. So it's 7x minus 0, which is just 7x. Very good. Okay, how we feeling? Let's set it up. Volume equals pi integral. Limits of integration are based on the original region. Since we're integrating with respect to x, give me the bounds on the region based on x. It lives from 0 to 1. Oh, I love it when we integrate from 0 to 1. So we have big R squared minus little r squared dx. How you doing? Excellent. Now let's multiply this all out. Pi integral 0 to 1. If I FOIL that out, it's going to be positive 49x squared minus 7 times 14 times 2 ends up being 14 times 14. So this is 196x plus 14 squared is 196 minus, I have another 49x squared dx. Ooh, these cancel. Great. And then look, why don't we just factor out 196? Look, look, look. It'll make life so nice. Take 196 out, 0 to 1. Then I have negative x plus 1. I'm just going to write that as 1 minus x dx. Isn't that less frightening to integrate? I mean, I just love it. Take out constants when possible. 196 pi, hanging outside, minding its business. Antiderivative of 1 is x. And then we have minus 1/2 x squared from 0 to 1. Leave the 196 pi outside. Look, it's happy. Don't mess with it. 1 minus 1/2 minus 0. So this is just a half times 196 pi is 98 pi. And voila, we are done. And that was so elegantly done. Do you know what I mean? I know when you're first learning, you don't think about taking out something like 196, right? But when you've practiced enough and you're not so overwhelmed, then you can really solve things elegantly. Yes. Okay. It's time to spin around some other lines, not just the x-axis, as much as we may love it. So find the volume of the solid generated by revolving the region about the given line. The region bounded above by the line y equals 9, below by the curve y equals 9 minus x squared, on the right by the line x equals 3, and we're spinning it about the line y equals 9. I know, you're like, when did math turn into reading comprehension class? It kind of always was, yeah. So let's see. We're bounded above, so that's the upper bound on the region, y equals 9. Below by the curve, y equals 9 minus x squared. Do you know what that looks like? 9 minus x squared, that's a parabola opening downward. And then we're spinning all of this around y equals 9. So I'm just going to stay kind of up here in quadrant 1. I'm going to say this is the line y equals 9. This parabola has vertex at 0, 9, and x-intercepts plus or minus 3. I'm only interested, though, in positive 3, and I'm going to put it all the way out here. Look at me again, scaling differently my axes, but it's going to be great. So this is 9 minus x squared. This is y equals 9. Okay. So I've got this curve taken care of, this curve taken care of, and then the line x equals 3, that's a vertical line. Can you see the region that's bounded by the given curves? So which curves were given? Y equals 9, 9 minus x squared, x equals 3. These three curves enclose this region. Not this one. Nobody said use y equals 0 or x equals 0. Do you see that listed here? I don't. Okay. So don't add new lines to bound regions that are not given to you. You can write your own problems one day if you want, but not right now. Sometimes the wording confuses people, so let me break it down for you. Bounded above by y equals 9. That means y equals 9 is the upper bound. It's bounded above by that line. below by that curve. That means that curve is the lower bound, bottom bound. On the right, by the line x equals 3. That line is on the right. It's the right boundary. And we're spinning all of this loveliness about y equals 9. Ooh, spinning that way. Here's y equals 9. So let's see if you flip it over. Oh, what? That looks vile. Hold on. Good. There's y equals 9. And then if we slice perpendicular to the axis of revolution, notice these slices are moving in the x direction. So we're going to integrate with respect to x. And there is no hole in any of these slices. So these are actually discs, not washers. We only have one radius. Can you see? Okay, so we're going to integrate with respect to x. And we have a disc. So what's the radius of the disc? Look at the original region before you spun. So do not look over here. Avert your eyes. Only look at the original region. There's the radius, is it not? Right there. That's the radius. Top minus bottom. Top minus bottom. Okay, so what's bounding the radius on the top? Y equals 9 minus, isn't this y equals 9 right there? Who's bounding the radius on the bottom? This curve. Who is this curve? It's 9 minus x squared. So 9 minus x squared, the 9's cancel. I just get positive x squared. All right, that's that. So volume equals pi. What are the limits of integration? They should be in terms of x, based on the original region. It lives from 0 to 3. And then we only have one radius, squared dx. Oh, not bad. See how the worst is certainly over. So this is pi integral 0 to 3 x to the 4th dx. This is going to be pi times 1/5 x to the 5th, evaluated from 0 to 3. 3 to the 5th, 243. So we have 243 pi over 5. Lower limit 0 just gives us 0. Done. Done and dusted. Okay, let's continue. Are you ready? Very good. Okay. Here we have, this is perhaps the spiciest one of all, grand finale. The region in the second quadrant, bounded above by the curve y equals 4 minus x squared, below by the x-axis, and on the right by the y-axis. And we're spinning it about the line x equals 1. What? I know. Do you know what 4 minus x squared looks like? Yes, you do. It's a parabola, opening downwards again. And it has vertex at 0, 4. Do you know what its x-intercepts are? Plus or minus 2, right? So here's negative 2, 1, 2, 3, 4, 1, 2, positive 2. So the parabola goes through 0, 4, 0, negative 2, and also 0, 2. 2, 0. What am I saying? Negative 2, 0, 2, 0. Okay, heavens to Betsy. Then they tell me we only are interested in the region in the second quadrant. Oh, okay, so goodbye. Goodbye. We're not interested in you. So sorry. Okay, so I've got 4 minus x squared. That's bounding the region above. Below by the x-axis. Okay, so x-axis, I see you. Here you are. And then on the right by the y-axis. So can you identify the region? These three curves bound it. Yes, do you see it? I'm going to shade it in right now. It's this little wedge right here. Beautiful. And we're spinning this, oh, this is different, about the line x equals 1. X equals 1, you say. Why, yes, we're spinning it around x equals 1. Here, Okay, let me draw what it would look like. Something sort of like this, okay? You know, it looks a wee bit, we were saying in class yesterday, like a bundt cake, no? Yes, kind of like a bundt cake. Now let's think, if we're spinning around x equals 1 and I slice perpendicular to the axis of revolution, my slices are moving up and down, aren't they? Up and down means I'm going to integrate with respect to y. Ooh, this is the first one where we've integrated with respect to y. Okay, so let's draw. Yes, we have a hole in the middle, right? We all agreed we have a bundt cake. So this is a washer. Ooh la la. Here's the washer. Okay. And then also, since we're integrating with respect to y, that means I have to have all of the curves and lines bounding the region represented as functions of y. So I need to solve for x right here. So y equals 4 minus x squared. If I rearrange it, that's x squared equals 4 minus y, which means x equals plus or minus rad 4 minus y. Now think about it. Originally, the parabola, I'm just going to do a rough sketch, was like this, right? Our downwards parabola. The right half is the positive rad 4 minus y, and then the left half is the negative rad 4 minus y. So right here, I'm going to choose negative rad 4 minus y to represent the curve, okay? Good. I think everything else should be clear. So let's go figure out what big R and little r are equal to. Remember, look at the original region before you spun. So don't look over here. No, it'll mess you up. I'm so sorry, but it will. Okay, so big R, here we go. From the outer edge to the center, big R. Now I know for all of the previous ones, we did top minus bottom. That's because we were integrating with respect to x. Now we need to do right minus left since we're integrating with respect to y. Just like when you first learned areas between curves, same thing. So here's big R, okay? What's bounding big R on the right? It's x equals 1. What's bounding big R on the left? X equals negative rad 4 minus y. I'll say it again. X equals 1. X equals negative rad 4 minus y. So big R is 1 minus negative rad 4 minus y. So that's 1 plus rad 4 minus y. Very good. Now what about little r? Little r sitting right in here. Do the same thing. On the right, we have x equals 1. On the left, we have x equals 0. It's just a constant. 1 minus 0. 1 minus 0, which is 1. And if you look, yeah, that should make sense because anywhere you slice, the inner radius is the same. It's constant. It's not changing. It's only the outer radius that's changing. Can you see it? So it makes sense. Little r is just 1. Okay, very good. And then when we set up the limits of integration, remember we're integrating with respect to y. So the limits need to represent the bounds on the original region in terms of y. So here was the original region, and it was bounded in the y direction by 0 and 4. So those are my limits, 0 to 4. So we're going to have big R squared, so 1 plus rad 4 minus y squared minus little r squared dy. Good? Okay, very nice. Now we're going to multiply this all out. So this is pi integral 0 to 4, 1 plus 2 rad 4 minus y. And if I square the last term, that's just 4 minus y. And then I have minus 1 dy. Does this clean up more? The 1's cancel. And then I just have pi times the integral 0 to 4. 2 rad 4 minus y plus 4 minus y dy. All right. Now, I was showing my class yesterday, you don't need to actually go ahead and do a full-blown U substitution just for this term. And I have a video talking about how and when you can skip U sub, okay? But it's basically anytime du is just a constant multiple of dx or dy in this case, you can skip it. You can skip it. And I'm just gonna do a little aside to show you, in case you haven't realized it yet, it will save you so much time, okay? So we know if you have, little integral y to the 1/2 dy, how would you find that antiderivative? You go, oh, it's y to the 3/2 divide by the new exponent plus c, right? If I switched it up and it was y plus 1 to the 1/2 dy, does that change anything? No. I mean, if you wanted to u sub, fine. U equals y plus 1, du is dy. So then you have u to the 1/2 du. Then you have 2/3 u to the 3/2 plus c. And then you just go right back to the original variable. So like what was ever the point, 2/3 y plus 1 to the 3/2 plus c. You could have just left it alone. You could have just left it alone, added 1 to the exponent, divided by the new exponent. Now, what if it's a little more involved inside, So what if we have integral 2y plus 1 to the 1/2 dy? Again, I'm saying you don't need to u sub. If you do, say you let u be 2y plus 1, du is 2 dy, right? So then 1/2 du is dy. And if you sat there and did all that, you'd have 1/2 u to the 1/2 du, 1/2, and then you have your 2/3 u to the 3/2 plus c, and then you have 1/2 2/3. I'll simplify that in a minute. I want you to see something. 2y plus 1 to the 3/2 plus c. So what happened? I want you to see this is not necessary. Whatever the coefficient was, we have to divide by it, right? When we do the u sub. So it just ends up there on the outside at the very end of the antiderivative. You really could have done all of this, 3/2, 2/3. You see there's a 2, just divide by it. Skip that whole u sub. If this was just sheer madness for you, okay, that's fine. Do the u sub. Then in that case, you're going to have to split this part up so you u sub that guy and not for these two, all right? I feel like it'll save you so much time and stress if you don't need to for something kind of straightforward like this. So the rule is, if du is just going to be a constant multiple of dy, simply divide by whatever the coefficient is. I'm gonna go for it. Are you ready? Okay, this 2 comes along for the ride. If I had u subbed and let u be 4 minus y, du would be negative dy, right? If u was 4 minus y, du would be negative dy. So that means I'm just going to have an extra negative. Put it right here. Then please leave 4 minus y alone. It's currently to the 1/2 power. So add 1 to the exponent, divide by the new exponent. Done. That's it. Plus antiderivative of 4y, minus antiderivative of y, 1/2 y squared. And we'll evaluate this from 0 to 4. Okay, it got a little crazy down below, so let me just move down. You got it? Okay, scoot, scoot. The mess was giving me some stress. Let's continue. Okay, so this is pi times negative 4/3. I'm going to plug in the upper limit right now of 4. Okay, 4 minus 4 to the 3/2 plus 4 times 4 minus 1/2 times 16 again. That's the upper limit. Minus, if I plug in 0 now, that's negative 4/3 times 4 minus 0 to the 3/2 plus 4 times 0 minus 1/2 times 0. Boom. Okay, let's see what's going on. So this is 0 to the 3/2, so this whole thing's 0. And then this is 16 minus 8. So I have pi times 8. This is going to give me plus 4/3 times 4 to the 3/2. 4 to the 3/2, how do you evaluate that? You take this root of 4, meaning the square root of 4, that's 2, and then you raise it to the 3rd power. 2 cubed is 8, so this is 8. Okay, so then we have pi times 8 plus 32 over 3. 8 is 24 over 3 plus 32 over 3. We have 56 pi over 3. That one was spicy, but I loved it so much. Did you love it? Should I put it on the exam, you guys, for Calc 2 this semester? I don't know. Okay. Anyways, I have more, but I feel like that's enough. If you would like to see more, comment down below. I could do a few more examples. I could do like another continued. I hope you found the video helpful. Let me know what your favorite part was. The graphs are essential. Always use the original region when determining the limits of integration and the radii. And subscribe if you haven't already. Give the video a thumbs up. I have full video lectures on my YouTube channel organized by playlists. I also have like quick tips, integral of the day. And then you can catch me on Instagram and TikTok too at Math TV with Professor V. I have to go, you guys. I have to go to yoga and then I have to go teach. So happy it's Thursday. I love Thursdays. And I'll be back soon. Bye.